This is the quiz on orbital diagrams and electron configurations. Most of these questions went pretty well for us. In question number 1, there is no such thing as a 2D orbital. The Ds don't start until the 3rd energy level. Question 2 is showing the valence electrons of nitrogen. So really all that was left off was the 1s orbital. When you have equal energy orbitals like P's and D's, we fill them 1 electron at a time before pairing if we had to. If you only have 1 electron in an orbital, the arrow is kind of arbitrary whether you have it pointing up or down. They just have to spin opposite if you have 2 electrons together in an orbital. Question 3 is showing the valence electrons of the nitrogen ion. If they're asking about an electron configuration or an orbital diagram for an ion, you have to take into consideration the charge. So as a -3 ion, nitrogen gains 3 electrons, and all orbitals are full. In question 4, they're asking about the electrons of an excited atom. So excited just means that there was some kind of an outside energy source that caused an electron to jump to a higher energy level or a higher orbital than you would expect it to be found. So something like the second choice, we should fill the 1s orbital before we put any electrons in the second energy level. So if I do have electrons in a higher orbital, we just say that it's excited. If you needed to identify the element, you can still just count the electrons. There are 4 electrons. This would just be some excited form of beryllium. Question 5 was a valid electron configuration. I would look for things like in the first choice, you can't have 8 electrons in a p orbital. In something like the second choice, just be careful when you go across that 4s2, 3d10, but then by gallium, you're back to the 4p for 3, if this one must be arsenic. In the second choice, if you're doing like a noble gas shortcut, just make sure that you have the previous noble gas. So if I'm starting with 2s2 in brackets, that should have been helium, not neon. So the last choice is right. Question 6 was fine. You could answer this a couple different ways. You could kind of figure out the charge, that if it's an element that ends 3p3, it's going to gain 3 electrons to fill its energy level, to fill the outer orbitals. Or you could just identify the element as phosphorus. And from there, I'm really just writing the formula of magnesium phosphide. And then at the end here, number 7 says, which of the following is paramagnetic? Okay, so paramagnetic means you have unpaired electrons. Unpaired electrons will cause an element to attract a magnet. Okay, so here's the problem with this. Paramagnetic means unpaired. The opposite of paramagnetic is dimagnetic. And that means all the electrons are paired. And so the problem is trying to think of a way to remember these two, because you think, okay, so paramagnetic. Oh gosh, does that mean they're paired or unpaired? And then you see dimagnetic, and you're like, oh, di, that usually means 2. So I don't know if this helps or not, but I kind of think, okay, dimagnetic, di means 2. So the electrons are paired. And then paramagnetic means they're unpaired. So I kind of think about it, this is the best I could do. Like PUP, it helps me. P-U-P. Para, unpaired. Paramagnetic means there are unpaired electrons. Di means 2. There are 2 electrons paired in an orbital. And for this, I think it helps to draw orbital diagrams, or at least think about orbital diagrams. When am I going to get unpaired electrons? often once you get to like the P's and D's, you have a better chance of finding unpaired electrons. Obviously, you could have an s orbital that's only half full. So if you kind of think about the electron configuration or the orbital diagram of these four elements, calcium should have everything full. So does zinc. All the P's and D's are full with 2 electrons. But oxygen will have 2 unpaired electrons in the 2p orbital. And so like liquid oxygen is attracted to a magnet. We don't notice it so much in the gas phase. If I had liquid oxygen, I could show you. At the end of the year, we'll bring in some liquid nitrogen, and sometimes that'll work too. Liquid nitrogen would have unpaired electrons, and that's attracted to a magnet. And so is manganese, lots of unpaired electrons actually. When you've got something that ends D5, we're going to put 1 electron in each of those d orbitals. Very magnetic. And finally, question 8. This was probably the one that was missed the most. And I think we're on the right track, that we can do the electron configuration of an iron atom. And most of us knew that +3 means to lose 3 electrons. But the rule for transition metals is that the 2 electrons you lose first are the electrons that are farthest from the nucleus. They're the ones that are going to experience the least amount of attraction to that positive nucleus. So even though the 4s electrons are filled before the 3d, because it's a lower energy orbital overall, because the 4s is a little bigger orbital, and on average, the electrons can be further from the nucleus, these are the first to go for any transition metal. The first 2 electrons lost are the 4s2. And so if I just had an iron +2 ion, I would only lose the 4s2. But now you can kind of see that iron's most common charges are either the +2, get rid of those 4s2, they're furthest from the nucleus, or the other really common form of iron is a +3 ion, because then I would lose one of these d electrons. This would then end 3d5. And there's something kind of stable about having all of your equal energy orbitals, like p's and d's, having them either all full or all half full, because then I don't have to worry about that repulsion of paired electrons. Oh yeah, if I had 5 electrons distributed amongst my d orbitals, each orbital gets 1. And so it should be the second choice. For transition metals, we always remove the 4s2 electrons first. And then if you have more electrons to remove, you can take them from the d's.